Welcome to the River Rock Dam Issue Evaluation Study presentation of findings to DSOG. The presentation will be divided by all members of our cadre, and as many are aware, our cadre numbers tend to dwindle, and we were happy to steal a member at the last minute on Tuesday. So our bottom line up front, the societal risk, incremental risk with intervention for AALL is 1.64 e to the minus 3. Kind of threw up the AAEC is there as well. The total APF is 1.81 e to the minus 5 with intervention with a average life loss of 91. The annual probability of life loss for the individual most at risk is less than the 1 e to minus 4 threshold. Our primary risk drivers are PFM1 spillway erosion and PFM2 BEP of foundation soils. Based on the assessment and background information, we're recommending a DSAC 3. The incremental risks are considered not tolerable based on the 4 TRGs. And this is one of our classic example cases with, despite both PFMs plotting below the guidelines, the total risk plots above. So a basic project overview. The River Rock Dam on the Warsaw River consists of a rolled earth fill embankment with an intake structure that feeds both power and flood control tunnels. You can see the tunnels right here outlined in red and blue, the dashes. These flow into the surge tank powerhouse and tail race for the power tunnel, and for the flood control pool, which just spills into our sealing basin. The switch yard, surge tank, and seepage berm with collector system are on the downstream toe of the embankment. The spillway is cut through the reservoir rim, so you can see it, the little arrow points 1.3 miles, and you can see the general vicinity of the dam versus the spillway over here. The spillway is comprised of an open cut approach channel, concrete line control structure with cutoff walls and foundation anchors, and an open cut exit channel. Both portions of the open cut channel are grass covered. The embankment is 1,100 feet long with a maximum height of 231 feet, and side slopes ranging from 1 vertical and 2.5 horizontal to 1 vertical and 3.5 or 3 horizontal. The central core of the embankment, as you can see here in purple, is impervious core. It's flanked on both sides by a fine random material in green, and then a subsequent coarse random fill material in yellow. And you can see on the furthest most downstream side, we also got a pervious fill material on the edge. On the downstream side, the embankment is underlain by a gravel drain that feeds into, and sand filter that feeds into the rock toe drain for seepage control. The embankment is well compacted, but has had historical distress associated with seepage near the downstream toe of the embankment or beyond the seepage berm. The foundation soils underlying the embankment are generally separated into 3 distinct strata. The first consists principally of stiff clay of intermediate plasticity with an occasional discontinuous lens of clayey or silty sand. The second consists of sandy clay of low plasticity and clayey sand. The third consists of silty sand and a poorly graded sand and gravel. Pool record here is 590.8, and as I'll go through the performance history later, it also had a pool of 590.7 as well. That's approximately 88% loading of the dam. So you can see I highlighted the control structure here. So the spillway is as shown in the previous image is a natural saddle in the ridge, 200 feet wide and 1,400 feet long. The control structure is 200 feet wide, so 200 feet this direction, and 50 feet long this direction. Reinforced concrete structure that is anchored into bedrock and includes both upstream and downstream cutoff walls that extend 10 feet into the bedrock to about elevation 582. The slabs of the structure are 2 feet thick, reinforced with 7 1/8 inch diameter bars at 12 inch on centers each way without water stops. The anchors are a 1 1/8 inch bar, drilled 8 foot into rock and set in 4 inch diameter grout holes, placed on 6 1/4 foot in centers. Though there was no seepage problems or drainage problems encountered during construction, the design included a drainage system, so it was placed under the structure to relieve hydrostatic pressure. This drain consists of a 6-inch perforated collector pipe surrounded by gravel and discharging through weep holes near the downstream slab. Unfortunately, the system has never been in video inspected, so the current condition is unknown. The downstream control structure, downstream of the control structure, the spillway has a slope of 0.005, has the same slope the other direction as well. Both are grass covered. As you get further to on the downstream side, about 750 feet down, you start to get to some hardwood trees and a few scattered pines. There's no tree growth on the upstream side, but as you can see right here with the contours, it drops off dramatically after 350 feet. Okay, the performance history. So in May '63, seepage was noted as soon as the pool reached elevation 528, which is 5 feet below top of conservation. A ponding area at the downstream toe at the left abutment indicating seepage was flowing underneath the dam. Luckily enough, it was low, widespread seepage, so there wasn't any evidence of piping, sand boils, or particle movement. Again, in the record event for May of 1990 that reached 590.8 during its way up to that pool in April 30th. A seepage boil was observed at the left abutment toe. Flow was measured originally at 20 gallons per minute, and within a few days there was 2 more pin boils observed in a similar case just 30 more feet downstream. The construction of a seepage berm and collector system was executed in between April and August of ~95. The seepage berm and collector system was designed and constructed as an IRRM in response to that historic seepage. The berm was designed to capture seepage, lengthen the seepage path, and prevent uplift, generally consisting of a 2-foot thick layer of sand overlain by 2 feet of gravel for additional weight. Unfortunately, in May 2015, the pool got back up to 590.7 again, and just beyond the seepage berm, 3 pin boils were observed. This were flowing. Later, a few days later, it increased to 7. So from that original 3 to 7. No damage was reported from these boils because they're similar as before, flowing clean without precipitating any fines, and the flow rate wasn't too high. And then it suggests that although the seepage berm, didn't control the seepage close to the embankment, it still just kind of pushed the seepage further downstream. But as long as they're still flowing clear, and future events will still be good. And then I will hand it off to Nathan for the loading.
Yep, thank you. So I'll go over the loading and the consequence information. So you can go to the next slide. So to develop the updated PMF, the HMR 5152 was used to determine the probable maximum precipitation for the dam. A site-specific PMP study was also performed, which indicated a PMP smaller than HMR 5152 due to current guidance saying to use HMR 5152. That's what was used, which indicated a 72-hour PMP of 29.8 inches. The PMP of 29.8 inches is a significant increase from the original spillway design flood. It's about 40% larger. The original spillway design flood developed in 1946 had a PMP of 21.5 inches. Detailed sensitivity analysis was performed on the PMF to quantify the range of potential inflows and pool stages, as well as to kind of determine what parameters the basin was sensitive to. All of the plans ran used antecedent event that was 50% of the PMF inflow hydrograph with a 5-day drying period between the antecedent event and the PMF. The recommended PMF has a peak inflow of 991,500 CFS, creates a peak pool of 618.2 feet, which overtops the dam by 2.4 feet. I think also should be noted that the antecedent event is large enough to initiate spillway flows. So on the graph we show here, spillway flows started approximately hour 60. The spillway flows continue for approximately 5 days prior to the PMF inflow affecting the dam. The pool remains above the spillway due to the limited capacity of the spillway, which is about 45,000 CFS. So that's pretty small compared to the antecedent event of 450,000 CFS, as well as, obviously the PMF of 992. The pool remains high because once the water starts to approach the spillway, the conduit's closed, so the spillway is the only way for water to leave the project. All right, so for the inflow frequency, as part of the inflow volume frequency analysis, the critical inflow duration for River Rock Dam was determined by evaluating the 1927, 1982, 2011, 2013, and 2015 floods. Critical durations for the representative events range from 2 to 3.5 days, with a final duration of 3 days being selected. The inflow volume frequency curve was developed using 95 years of systematic data from 1923 to 2018. There was historical data available for major floods prior to the dam construction. So those consisted of December 1848 to May 1871 and May 1882. The May 1882 flood was incorporated into the inflow volume frequency analysis as a historic flood with uncertainty. There was also regional skew data available for the project site from a USGS report. So that information was also included in the analysis. The regional skew value was for a peak inflow, which was determined to be appropriate for a 3-day critical duration. So it was used to inform the weighted skew at the dam site. And then to further improve the inflow volume frequency estimate, a precipitation frequency study and a paleo flood study were both performed. The 3-day rainfall runoff analysis for the precipitation frequency study used Atlas 14 data at an AEP of 1e to the -4. So that information was used to help inform the curve. And then lastly, the paleo flood investigation was performed to estimate the magnitude of any prehistoric events that might have happened on the Warsaw River. The results from that study showed evidence of a large prehistoric flood between 1,000 and 5,000 years ago, with a best estimate 3-day inflow of 108,500 CFS and an approximate age of 3,200 years. Furthermore, a non-exceedance bound was also discovered. And the non-exceedance bound has a best estimate 3-day inflow of 218,600 CFS with an estimated age of 7,200 years ago. I think it's worth noting that 218,000 estimate is below the 3-day PMF runoff volume. I also wanted to point out that the AEP for the PMF based off the inflow frequency curve is approximately 2e to the -7, with the upper uncertainty closer to 1e to the -6. All right, so RMC-RFA was utilized to develop the final stage frequency curve. RMC-RFA uses inputs such as inflow volume frequency, daily stage data, flood seasonality, historic hydrograph shapes, reservoir operations, et cetera, to stochastically predict the stage frequency for the dam. The stage frequency curve plots well with the observed annual peak flows that are plotted there. So the plotting points used were from 1970 to 2018. Typically for stage frequency curves, we'll see an inflection point at the spillway crest. This one does not have much of an inflection point, which I think kind of makes sense due to the fact of the relatively small spillway capacity of 45,000 CFS. Generally speaking, that's pretty small compared to most of the dams in our portfolio. So the PMF peak stage of 618.2 feet has a best estimate AEP greater than 1e to the or less than 1e to the -8, with the upper uncertainty also less than 1e to the -8. Confidence in the loading curve is moderate to high due to the inclusion of the Tier 2 paleo flood information, regional skew, and precipitation frequency data. So we've done a fair amount of study for this project, and at this time we wouldn't suggest any additional hydrologic hazard studies moving forward.
Nathan?
Yep.
Go back one slide, yeah. How do you feel you said that the historic data fits the curve well. Can you explain those points at the low end of the curve where it deviates?
No, that's something we could, often with RMC-RFA, will kind of tweak reservoir operations to try to get things to fit the plotting positions more frequently. At those really frequent ends, we're not as concerned with how well the curve's fitting our plotting positions. Generally speaking, we're much more concerned with the more frequent, or I guess less frequent, sorry, side of that. I will point out, so the plotting positions we use were from 1970 to 2018. So the fact that, you know, some of these dams, when we have historic floods, we'll route them through the project to see what stages they would have created. So there are probably some opportunities to try to better understand some of those stage plotting positions if we did a little bit additional work. But specifically from that 0.9 AEP to more frequent, I do not have a great explanation for why the curve is not fitting those points.
Okay, thanks.
All right, so we don't have any risk driving failure modes that use seismic hazards, so I'll go through this pretty briefly, but just wanted to include the information. A local PSHA has not been performed for the project site. There's considerable uncertainty for the AEPs less than 1 over 10,000. Like I mentioned, the risk driving failure modes don't use the seismic loading. However, I did want to point out for reference that the operating base earthquake with a return period of 144 years, the PGA of 0.02, and the maximum considered earthquake with a return period of 2,475 years with a PGA of 0.1. Next slide. All right, so consequence overview. So I'll kind of go over the consequence as a whole, and then with each failure mode, we'll kind of dig into those a little bit more. So these are the breach parameters that were used for the spillway erosion failure mode. Generally speaking, the breach parameters were not varied for the different pools that were considered. The only variable that changed from the different loading conditions was the breach trigger event timing, which was based on when the head cut reaches the control section, and for the analysis was assumed to be 4 hours after the flood peak for each of the loading scenarios. So that time will change from scenario to scenario. The peak breach outflow was not significantly greater for the compared to the non-breach scenarios for this failure mode. You can see the incremental flow released from the dam varies for the different pool elevations, but was generally between 33,000 CFS for the 594 peak pool, and then upwards of 53,000 for the 615.7 peak pool, which is the top of dam. So, you know, relatively small incremental releases from the dam due to this failure mode. Next slide. That's quite a bit different for the backward erosion piping failure mode of the embankment. Pools were looked at starting at the normal high pool of 578.7 up to the top of dam elevation of 615.7. So this table does have runs for the PMF and the upper PMF. However, those scenarios were not used as part of the backward erosion piping risk calculations. The breach development time for all the scenarios ranged from 3.3 hours to 4.3 hours. And they did vary the bottom width of the breach based off of pools greater than or equal to, or sorry, lower than or equal to TAS. They used the 791.4, and then above that, they used the 660 feet. Like I mentioned, unlike failure mode 1, the breach flows for the various pools analyzed for this failure mode are significantly higher. The top of dam scenario results in incremental breach flow of 7.6 million CFS. And the normal high pool scenario results in an incremental breach flow of 5.3 million CFS. So as can be expected, this failure mode will result in significantly higher PAR being affected and much higher incremental consequences, which we will go over on later slides. You go to the next slide. Okay, so our downstream consequence centers mainly focus on the city of Willow Forest, the city of Oak Point, and then Glenn County and Willow Forest County. We did have a consequence elicitation performed with these different groups. Willow Forest and Oak Point are located approximately 10 miles and 38 miles downstream respectively, and they have flood wave arrival times of 1 to 3 hours respectively. So kind of going back to that seismic failure mode, we have a pretty sizable flood wave coming through that gets to these consequence centers very quickly. Flood depths in the Willow Forest area during this embankment failure are anywhere from 11 to 70 feet, and they are 3 to 30 feet tall in the Oak Point area. It's also worth noting that both of these consequence centers have medical facilities and nursing homes that would be impacted by the larger releases of River Rock Dam. And so I know this slide's pretty wordy and goes over a lot of the communication that happened between the different groups. But I think one of the key takeaways here that we wanted to point out was the approximately 9,000 PAR for the River Rock Dam pool for the nighttime failure modes. That's using the upper PMF inundation. A significant portion of those people are over the age of 65, so evacuation is a little bit more limited. And next slide. So now I'll go over the consequences for the two failure modes. So this slide covers the breach, non-breach, and incremental consequences for the spillway erosion failure mode. It includes both the life loss and property damage. The property damage is based on the 2018 price level, so that is something that could potentially be reviewed and updated if future studies were to occur. No incremental life loss consequences are expected at or below a pool of 597, so we thought that was a pretty key takeaway here. Incremental life loss peaks for a pool of 610, with 16 expected for both day and night. You can note that the non-breach life loss for the top of dam loading condition is significantly higher than the 610 pool, so that's why the incremental consequences are lower for that top of dam failure mode, is due to the additional flooding from the top of dam condition. Next slide. So this just shows our whisker plot of the life loss. So I think the whisker plots can often help to visualize how incremental life loss can vary. So this just kind of shows how the life loss varies for the different pools analyzed. As you can see, the life loss varies, quite a bit. So at the lower pools, we're not capturing, any of the 25th percentile, for example. Whereas when you get into those upper pools, you can really see how the consequences start to increase. Next slide. All right. So these are the consequences for the backward erosion piping embankment failure. Which, kind of what I alluded to previously, the numbers are significantly higher for this failure mode than the spillway failure mode. Again, we did not use the upper PMF and the best estimate PMF for the risk calculations. We limited the backward erosion piping failure mode to the top of dam pool. But as you can see here, incremental life loss is significant for the various pools that we analyzed and range from approximately 3,000 up to 7,500. All right, so this is just the kind of similar, whisker plot for this failure mode. Obviously, you can see very high consequences that all, for all scenarios, essentially range between 1,000 and 10,000 lives lost, which I think can probably be expected due to, like we mentioned earlier, the significant breach size, tall dam with a lot of volume of water, and two consequence centers being located very close to the dam. And then lastly, I'll go over some maps. I'm sorry, you can go to the next slide. Yeah. So this just shows the spatial distribution of the consequences, so the heat map for the spillway failure mode. So this specific plot is for night life loss with the top of dam loading. We have the PAR listed there as well. I think where this can be helpful is just kind of comparing this to the next slide. So if you want to go ahead and go to the next slide, you can see that there's drastically more people affected for the embankment breach. This plot is for the upper PMS scenario. So we're kind of limited on what maps we had available to include here. So we didn't end up including this upper PMF embankment breach in our inundation. But this just kind of, I think, helps to visualize where the life loss is happening downstream. Okay, next slide. Almost through the consequences. So just kind of help visualize this in a different way. So this is the top of dam inundation downstream of the dam. So on the left shows the dam in the up top left with the city of Willow Forest down to the bottom right, and then the right-handed figure is for the city of Oak Point. So this kind of helps visualize how the inundation boundaries between the breach and non-breach scenarios are very similar for the spillway failure mode, which makes sense with the limited incremental releases from that spillway breach. And then lastly, we have a plot. If you want to go to the next slide. We have a plot of the TAS inundation for the backward erosion piping and embankment failure mode. So these numbers are for the upper PMF scenario. So these depths aren't as drastic for some of the other scenarios, but 10 miles downstream with a 1 hour arrival time, we'd see a flood wave of 11 to 70 feet, depending on what scenario you're looking at. And then at Oak Point, which is further downstream, 38 miles downstream of the dam, with an arrival time of 3 hours. Those flood waves have inundated a little bit, but are still, very significant with upwards of 30 feet of depth there. So that's kind of a general overview of the consequences. I made it through that without sneezing 17 times, which has been the story for the day. So I'm happy about that. And I will hand things off to Jamie.
Thank you. So we have two risk driving failure modes for River Rock Dam. So we'll jump right into the first one. The first PFM one is spillway erosion. This image shows a good overview of the spillway, and you can see the good grass cover. Unfortunately, this location was picked due to its convenience during construction in terms of material removal, as well as proximity to the river for outlet, rather than the foundation materials, which I will get into on the next slide. And I just want to point out on this overview also the location of the control structure, which we've already talked about a little bit, and which has the protection features of the cutoff walls and anchors. And the distance between the control structure and the upstream sill is just approximately 350 feet. It's a little bit difficult to see in this image, but along the left side of the spillway is a access road as well, and that is the spillway access road in the spillway. So that serves as a low point as well as a limitation for intervention. So on our next slide, we have the event tree, and the IES team envisioned this failure mode developing by starting with the removal of grass cover 750 feet downstream at the tow area. Wind dam modeling showed that grass cover would be removed rather quickly when compared to the spillway duration flows, which exceed 22 days. So the team considered the removal of the grass cover to be very likely. For head cut initiation, the downstream material under the grass cover is the residual soils that have a low head cut erodibility index. Various methods for estimating whether or not these would initiate all showed that there would be initiation of head cut erodibility, and so this node is also very likely. Node 3 and 4 were informed by wind dam modeling and other erosion analysis, and these nodes were more pool dependent. The model showed that for elevation 602 and above, there was more than adequate flow duration to advance the head cut to the control structure, and also adequate flow duration to undermine the control structure as well. For intervention, as I pointed out on the previous slide, the access road is in the spillway, so when you have spillway flow, access is very limited, as are your means for intervention. One way that intervention could occur is by using the outlet tunnel to increase flow. It's typically limited to 3,000 CFS, but has a much greater capacity, so that could help offset inflows. And there's also a possibility to place materials via helicopter. However, intervention is less likely in general to be successful as flows increase. For the breach node, this was also informed by wind dam modeling and estimated advancement rates for that additional 350 feet of residual soil to get to the spillway crest. The models show that there's more than sufficient time in the hydrograph left after undermining the sill, after undermining the control structure to progress the failure mode all the way to full breach. However, this is dependent on the pool you're evaluating and whether or not you have time left. But there's approximately 900 hours left, which translates to over a month for elevation 602 and above. So that's the type of durations we're talking about. Next. So the annual probability of failure is 1.79 e to the minus 5 with intervention, 3.69 e to the minus 5 without intervention. There have been no spillway flow events, so the SRP is informed primarily by the modeling and the analysis that was performed to determine if the residual soils and foundation rock would erode and undermine the control structure. There may be some variability in the foundation materials, which could potentially be a source of uncertainty. And the team also considered to counteract that with the driving force behind these nodes being those extra long durations. There is some uncertainty in the loading. There's 2 orders of magnitude uncertainty in the stage frequency for pools 602 and above, which were those critical pools. And next up is the life loss. So the average life loss is 7 without intervention and 8 with intervention. There, as previously mentioned, there was a consequence solicitation which was used to inform this. Each pool considered, and shown here, we did a sensitivity. There's a 95th, 75th, 25th, and 5th percentiles. These are the median values shown. And the biggest source of uncertainty with our consequences was considered to be the breach parameters.
Hey, Jamie.
And
Got a quick question.
yeah.
So,
sorry, I thought I heard that.
Yeah, can you hear me?
Yes.
Okay. Yeah, so what was the plan for intervention on this one? I'm just curious. The ungated spillway, I was just curious what the plan was, or if you guys talked about it at all.
Yeah, so there was discussion about the use of the tunnel because there's capacity there, but only up to a certain stage, at which point it would become overwhelmed because there's about 20,000, over 20,000 CFS in capacity, and it's usually operated around 3,000 CFS, so you can get some offset there to help reduce flows. And they also have an agreement with the National Guard to have access to a helicopter, and there's large materials that they could get that's 50,000 miles, or 50, not 50,000, 50 miles away at a nearby quarry, but they aren't sure if the helicopter can actually carry that rock, so it's a conceptual plan. So as far as intervention, besides operating the tunnel, there's not really any value, and there's not really anything concrete.
Okay, thanks.
No problem. So uncertainty is, just to reiterate, is the breach parameters. They assumed a fixed breach geometry and breach formation time for all pools, and due to the different depths and durations, the breach geometry may be different. However, it doesn't seem to have a huge impact since the incremental releases relative to the non-breach releases don't show much difference. So,
how do y'all feel about the assumption that breach initiation is going to occur 4 hours after the peak for each flood event? It seems like each flood event is going to bring different amounts of flow. Does that 4 hours across the board seem adequate?
I'll chime in. I think it I don't know, maybe seems a little bit suspect. We could probably run some additional sensitivities to that. I think generally speaking, we were thinking that, you know, varying the breach formation time as well as when the breach started to form could be something worth doing to just understand how that sensitivity performs. But kind of the end answer we kept coming back to was the spillway breach size seems to be relatively limited. So we didn't think the consequences would be very sensitive to running those additional sensitivities to breach formation time and when the trigger occurs.
Okay, thanks. That's a good explanation.
okay, stepping forward to the economic cost. The average annual economic cost was $847 without intervention and $479 with intervention. This was developed for the residential structures using the guidance memorandum and to develop the depth damage curves, and for the non-residential structures, the default USACE curves were used. There could be uncertainty as to how these curves actually correspond to the actual cost. And additionally, the price values are based on 2008. And as we all know very well from our daily lives, the prices have gone up significantly in the last 4 years. So they're likely underestimated based on that as well. Any questions on failure mode PFM1? Okay, so potential failure mode 2 is backward erosion piping of foundation soils. There's available boring data and gradation data that indicate there is a cohesive blanket layer of approximately 15 to 20 feet thick, underlain by a granular zone upstream to downstream across the dam footprint, as shown. And there was CPT and boring data that both verified the existence of this granular zone, and within it, a zone with poorly graded sand that also had a low coefficient of uniformity. And those are called out in the underlying drawing as low CU sands that you can see. So the event tree shows that the failure mode depends on for the flaw node, depends on the existence of this continuous DVP susceptible layer from upstream to downstream. There is gradation data that indicates there are materials in the foundation with a CU less than 6 that are susceptible to BEP. However, there's variability across the material, across the footprint, and the flaw path is approximately 1,000 to 1,200 feet long. So it was concluded by the team that it was very unlikely to have a continuous zone of erodible material. If there was, the most likely exit for seepage is immediately downstream of the seepage berm toe, where there is no filter. Past flood events have yielded seepage and pin boils, indicating that the confining clay layer contains defects, and so this node was considered almost certain. For nodes 3 and 4, the critical gradients for the BEP susceptible material for initiation and progression were compared to for initiation were compared to linear piezometer projections, which showed that the BEP initiation would be very unlikely, and the same was shown for progression when compared to the average critical gradient, or average gradient, sorry. For the node 5, the soil investigation showed that 41 of 42 samples from the upper foundation soils had a fines content greater than 15%, with the average being approximately 61%, making the materials overlaying that sand layer likely to hold a roof. For intervention with the BEP failure mode, the dam is under 24-hour surveillance when the pool is above 585, which is approximately 10 feet, 15 feet below top of active storage. And the project personnel do initiate monitoring activities if boils are observed. But when pools exceed top of active storage, the downstream area is likely inundated by tailwater, reducing the ability to detect signs of distress. For pools above top of active storage, it's very likely that intervention will be successful, but for lower pools, will be unsuccessful, but for lower pools, past performance shows that project personnel can successfully intervene and arrest pinboil activity. So for the breach node, once the EP progresses to the reservoir, there's no geologic feature that would prevent growth enlargement and progressive collapse from leading to breach. So the likelihood of breach is dependent on pools, since the collapses of the embankment have to exceed the coincident pool in order to lead to breach. So the annual probability of failure is 2.35 e to the minus 7 with intervention, 3.73 e to the minus 7 without intervention. As mentioned previously, in 2015, the pool raised to a near top of active storage elevation, and there were 3 pin boils observed at the downstream toe of the seepage berm, and there was no movement of fines. So despite evidence of seepage, past performance shows that the BEP is unlikely to initiate and progress to failure, and that's reflected in our SRP. The significant sources of uncertainty are, again, the variability, the uncertainty in the stage frequency, and more significantly, the continuity of that potential BEP susceptible material from upstream to downstream across the dam footprint. The life loss, the average life loss is 6,350 without intervention and 6,374 with intervention. I think I might have said with both times, but hopefully y'all can read. Similar to PFM1, this was informed by the consequence solicitation, and each pool for the breach scenario was estimated with uncertainty in LifeSim. Note that the upper PMF and PMF were not considered for this failure mode. And for pools above top of active, unlike PFM1, there are large incremental releases for this failure mode, but similar to PFM1, there's uncertainty in the breach parameters. Again, one breach geometry was used for pools above top of active storage and another below. And again, there's probably some variability in that based on the actual flows and the actual depths and durations. There would be some variability in those breach parameters, more so than what was modeled. The economic cost, the average annual economic cost is 1,740 without intervention and 1,100 with intervention. These were developed using the same methods as PFM1 and therefore have the same sources of uncertainty. As you would expect, the costs from the dam breach are significantly greater than the spillway failure. And are there any questions regarding the failure modes before we move on to the risk estimate? All right.
Okay. So I'll jump back in and take over the risk estimates. So next slide. As you can see on this societal incremental life safety risk plots, we have with and without intervention, and the uncertainties for them both plot up as totals plot above the societal risk guideline. But as you can see in the big FN charts, it's really pulled from the 2 points that, the spillway erosion that plots over here in the underneath the societal risk guidelines, and then the BEP failure mode that falls right here in this high consequences, low probability box. So the incremental life safety.
Andrew?
Sure.
Quickly, before you move on, as
Yes, sir.
it relates to the total risk, and then I guess specifically for PFM 1 and 2, can you give a brief rundown of what pools are driving the risk, what pool ranges?
Sure.
Say while he's pulling that up, I might be able to help, but for the spillway erosion failure mode, 605 up to the top of dam, 615.7 are driving the incremental risk. A pool of 602 has 1 life loss, so that's kind of our inflection point. Pools below 602 don't show any incremental life loss. And then we'll see how quickly I can find the same table for the backward erosion pipe.
So you said that all the way up to top of dam was providing significant contribution to the risk?
Yeah, I mean, I guess it kind of depends on how you define significant. So 610, the pool 610 has the highest incremental consequences at 16, but the top of dam has incremental consequences day and night of 4 and 3. So I guess it's not 0, but the top of dam is slightly lower than 610, and that was due to the larger non-breach life loss at that
Well,
pool.
but what about in terms of average annual life loss? We can look at consequences, but unless we marry that together with hazard and system response, we don't really know what's driving the risk. Do you guys have risk profile plots?
Yes.
Yeah, so looking at that, where are we getting the majority of our risk contribution from? What pool range?
The 580, so I believe, as Nathan said, so 585 and above.
So remember, a flat line means that no.
Or am I looking at?
I think you're looking at the right plot.
Okay.
I think he's asking for the change in slope here. So the big break in slope, right? Isn't
Got
that
it.
what you're honing on, Adam? This.
So that's part of it. But remember too, this is a log scale, so the greatest slope doesn't always mean the greatest risk contribution. I'm asking you, looking at this plot, where is the majority of the risk coming from? So for example, if you draw a straight line down around pool elevation 596 or so, the curve flattens. It's a straight line for all pools above 596. So
Yep.
that's an indication that you're not really getting a lot of risk contribution from pools greater than that elevation. So that's the question that I'm asking, is where you're which intervals of pool are really driving the risk once you put together your AEP, your performance, and your consequences?
Yeah, so I guess for this failure mode, it would be pools below about 585, I guess between 575 and 585.
Remember, it's a log
It
scale
looks
down
like
there, so.
it looks like 584.5 is this where it goes from looks like what 580 578.7 is what we listed. So that was like a 0, and the 584.5 is where it comes up here to actually be a point near where it starts to make the break. So it looks like it's from 584.5 to that 605 numbers where we're getting this turn in the curve, and that's where our risk's coming from, right?
I'm seeing the 584. I'm not seeing the 605. I'm seeing like a 595.
Oh yeah, I'm sorry. I just can't view it that well because I need to zoom in a little bit more. Sorry.
Yeah.
But yeah, where the curve goes from that last point, and it actually makes like an actual curve as opposed to just connect the dots. So where it breaks over.
Yeah.
So that range of it there.
Yeah, I agree with that. That's what I was saying on Monday with the log scales. It's kind of hard. You can't really trust the severity of the slope. 1e to the minus 10 plus 1e to the minus 4 is still less than 1e to the minus 3. So, I mean, you just have to take that with a grain of salt. Okay. And is it similar for PFM1?
On page 65 of the PDF.
Thank you. Short answer, no.
What's the long answer?
Well, it looks like it pulls in almost all the values because the range we elicited was 594. So that looks like that's the first real value from the 0 to boom. It's about 594, and then it breaks over at 602. So 594 to 602 is the arc here.
Yeah, I would roughly agree with that. Maybe a few feet higher on the lower end, but inconsequential. All right, so good. About 587 to 595 for PFM2 and about 594 to about 602 for PFM1. All right, thank you.
Thank you, Jamie,
No problem.
for sharing that. Okay. Okay. So the individual incremental life safety risk, the individual most at risk lives in a primary residential area mixed between single-family, single-story homes and 2 to 3 story multifamily homes within the first 3 miles. But as you can see, the plotting position is below the individual tolerable risk limit. Okay, so non-breach life safety risk. You can see that the plot kind of here, if you remember the incremental, it kind of falls well below the incremental, which was more of a curve like this. So it's not the largest contributor to risk. But you can see non-breach is pretty much driving the economic consequences as the main factor in that. But I want to kind of go back to here. We kind of talked about the flooding threshold. They were kind of trying to manage the flows to 3,000. So that kind of sets our thing where we start to have some flooding and damage. but we're not really seeing any life loss even on the non-breach till we get to a return period closer to 1 in 200,000. And then for econ. Okay, so the DSAC. So the total with intervention plots right here in this green dot. I don't know why my arrow line moved over, but right here in this green position, we think it's well within this scatter of 3s and 4s, but it kind of tops out closer to the 3 range. Some argument also kind of think if you kind of transition with that other range that kind of gave us where the BEP failure mode, it would kind of kicked out somewhere over here. So we'd probably still kind of be in that 3 range for that failure mode. So I thought we were confident in our 3. So again, based on the hydrologic modeling, the site-specific consequence elicitation, and thorough evaluation of the properties and available data, the team recommends a DSAC 3. So for tolerable risk guidelines, the TRG1, so the individual is met. Unfortunately, the societal is not. There's that kind of in the presentations earlier about whether these kind of historic one might be maybe, but we kind of went with, based on the other plotting positions and some of the other concerns, that we should go with no. The economics are not, changing the nation enough to warrant that. There was no great historical or cultural sites that were identified during the assessment, and that have risks been reduced as low as reasonably possible? Probably not, because we could get ourselves out of this box. So building risk awareness. So the project has conducted tabletop exercises every other year with FEMA, with but they missed the most recent one due to COVID. So they should be on track to do another one next year. The internal risk communication workshop was also held in March 2020, but the USACE maintains Facebook page for the dam to communicate public concerning all these other life lessons and whatnot, but not really specific to between USACE and the public, and communicate specifically to the population. So though the district is planning to communicate the results of the IES to the local EMA and public with a focus on this, they have no, like with other talks earlier, there's no timeline specific to when they plan on doing that. And they haven't done it yet, so we feel that it's still not met. So fulfilling daily responsibilities. The NID scorecard for the Rock River Dam is 80 out of 100, which is, fairly good. For some people it's a B, some people it's a C+. So the EAP has been updated on a regular basis, but it needs to be updated based on IES. But based on there not being the site-specific safety training has not been performed in the last 5 years, they haven't been keeping up with some of their, FY consistent dam safety seminar and exercises. And then the PI report is kind of stole from some of my thunder from the last presentation when it was kind of a question, is that they were well past the grace period enough to where they got 1 out of 12. So I don't know whether that means they just actually produced it as opposed to didn't, with some of these other like PAs that are, outstanding for years. But we thought this shows like a consistent basis of not meeting the dam safety specific stuff that were expected for daily responsibilities. So we decided it was not met. That TRG4, so the project IRMP was created in 2009. You can see that they've executed a number of IRMPs, RMs, and then they have some follow-up ones based on the IES. So I think based on their history of actually executing these, and they're planning to do more, that they'll actually execute these. Whether they'll actually do the other trainings, maybe not so much. So we think TRG4 is met. The path forward. So we recommended evaluating some alternatives in a DSMS with due consideration for risk communication and non-structural measures. So do some more stuff associated with what kind of warnings, or even some, maybe look into getting out warnings when and start mobilizing people downstream when you have depending on the level of distress, rather than just waiting till you know it's going to be a breach. So we could, communicate with the public to try and see if that's something that they're willing to entertain. And then recommendations, again, update the IRMP with the new elements, perform a site-specific training that they're supposed to be doing, and get up to speed back up on those seminar and drills. There we go. Any questions, comments, or discussion?
I don't think we have any, Andrew. Thanks to Group C. All right, Groups D and E. Go ahead and log into Socrative and vote.
If you could go back to there you go.
I'll leave my cursor over where it's supposed to be at for a bit so people can see it until they want me to advance the slide. It should be where the cursor's at.
Could you advance to the TRG1 slide again, just when you get a chance? Thanks.
Sure. I was wondering if this might be helpful if I just kind of show, here's 1, 2, 3, and 4 at the same time. You may or may not be able to read what I'm sharing, but.
That's helpful to me, thanks.
All right, so it looks like unanimous 3.
Did anybody give consideration to the big FN plot when they were looking at DSAC?
Oh, yeah.
Both
F. We use both F's.
Anybody?
Little F and the big F.
Anybody think about the big FN chart at all?
I don't know if this is what you're getting at, Adam, but I know one of the things we talked about as a team was kind of the concept that both failure modes individually plotted below the line.
Nathan, we lost you there for a few seconds.
Okay. Now, basically, I was just saying, I don't know if this is what you're getting at or not, but when you look at the failure modes individually, they both plot, much lower, but it's when you combine them together, you have one with a high AP with low life loss and one with a low AP with high life loss, and then combined, they plot at that 3 range. So is that kind of what your takeaway from the big FN plot is, or should be?
Yeah, that's what I'm asking about. Is this an instance where a single point doesn't truly represent risk? And was that considered by anybody when looking at either DSAC recommendations or at TRG1?
It's something we definitely discussed as a team. And I kind of looked at it through a lens of when we go to make recommendations, affecting one versus the other would, affect the risk differently, to try to think through that. But I don't know. I guess I'll let everybody else chime in. But I didn't necessarily use it to inform my DSAC recommendation. I based that a little bit more off of kind of where we were plotting as a total.
I kind of looked at it a little bit, Adam. I mean, with both failure modes, I mean, you kind of got to look at the total risk for DSAC. I mean, both of them independently were under the threshold, but both of them together were over. So anyway, I kind of looked at it a little bit, but looked at mostly the combined little FN chart for my determination.
Yeah, so
And they could occur simultaneously, right? You could have both occur. They're not mutually exclusive.
Yeah, I see that. I want to caution against only looking at the little FN. I mean, there was an example of a project in the USACE inventory that looked just like this in the last year or two, plotted in a very similar location and was classified as a DSAC 4 because of the big FN considerations. So yeah, you look at both. You look at the total risk and it plots above the guideline, but you do have to give consideration to the big FN as well, because the little FN it sometimes isn't the best vehicle to communicate risk when you have two wildly different PFMs. So
in your example, Adam, were those failure modes exclusive of each other? Not dependent on each other, or not depend, you know what I'm saying? So here we have same types, once you got over the spillway, you could have it breach while the other failure modes occurs. They could both happen. Was the other one that you're talking about, was that the case? Or, I think if these were two independent failure modes that neither one could occur in the same scenario as the other one, then it might be more likely to give it a 4. But I think since both of these could occur simultaneously,
Yeah, I see what you're saying, Greg, and that's a good consideration as well. And honestly, when you look at the plot, the portfolio plot, you could make the argument that if you were looking at either one of them independently, you could assign a DSAC 3. I was just curious to see if anybody had looked at the big FN and wanted to throw that out there, that there are scenarios where we can't just look at the little FN and make a determination based on that alone.
right?
Yeah, because that last argument you were describing, Adam, was what I tried to make during the presentation, is that independently each one would still plot right in line with the orange boxes for DSAC 3. If only BEP was your only failure mode or the other one was your only failure mode, it would still plot in the general area of 3s.
All right, let's go to TRG1. All right, so we have unanimously not met for TRG1. So this is another interesting one. If you remember back to the TRG1 slide from the other day, we do have a consideration of maybe for projects like this where you have a little FN that plots greater than 1e⁻3, but at the same time you have a big FN that does not exceed the 1e⁻3 line and plots within that low probability high consequence zone, and that's classified as a maybe. So Andrew, I think I heard you say something about a maybe zone when you showed the TRG1 slide. I'm curious, did anybody else take that into consideration?
There was no maybe answer.
No, I'm not talking about a maybe answer for tolerability of 1. You're right. There was no answer. There was no maybe answer on Socrative. I'm just wondering if that played into anyone's decision making, because ultimately, even if this were, even if they said maybe, we would still have to vote tolerable or not tolerable, one way or the other. So that maybe there, that indicates that there's a portion of the risk that's plotting in the low probability high consequence zone, and really what that means is that it brings a higher standard of care. It requires a higher standard of care to meet tolerability. So if we plot down in that box, in that low probability high consequence box, then we need to ensure that we are very confident in our characterization of the risks. We're confident in our in our ability or our history of reducing risks as much as possible, just making sure that we're doing everything that we can to treat those risks with the high priority.
I guess, does everybody understand what this means? Because I'll be honest, I didn't until about a half hour ago. And does anybody want to walk through that?
It's definitely something that can be kind of confusing to me as someone that doesn't deal a lot with risk calcs and AALL and ATF and big F and little n and all that fun stuff. It can definitely get a little bit confusing at times.
Can you explain it real quick,
Yeah, so we can walk through it. So let's look at the second maybe right there, so that bottom maybe. So the first criteria, average annual life loss is greater than 1 × 10⁻³ . That's our typical average annual life loss that's associated with the little fn chart. So the middle chart to the right. Along with that, it's saying APF is also greater than 10⁻⁶. So that qualifier is in there to ensure that the average annual life loss plots above either the sloping 1E-3 line that Carmen's highlighting right now, or the horizontal low probability high consequence line at 1E-6. However, as is with the case with River Rock, we also have another consideration where we say, but the big F is less than 10⁻³ divided by n. So when you look at the chart on the right, that's your big FN chart. So any point along that curve is equal to the product of the F on the y-axis multiplied by the n on the x-axis. So it's the probability that F is greater than a given n. So when you look at that curve, when it says F is less than 10⁻³ divided by n, it means that at no point along that curve does the curve exceed the societal risk threshold limit of 1E-3. At the same time, there's another qualifier there that says big F is less than 10⁻⁶. That's to cover the low probability high consequence box. So essentially you're saying, just as the first part is ensuring that the little FN plot is above the sloping line or the horizontal line, the bottom part is ensuring that the big F or the big FN line is below the horizontal sloping line, or I'm sorry, the sloping line or the horizontal line.
Okay, so we're looking at there.
Yeah.
But in the
If you
case
fall
of,
in that zone, then you're still considered tolerable?
Maybe.
maybe,
So that's where the maybe comes in.
How do you associate maybe with met and not met, I guess that's what I'm confused about.
Yeah, so that's the difficult part. That's what I was talking about with the higher standard of care. So in that case, we need to look at the dam itself, about the operability of the dam, about the standard of care that's taken at the dam, to determine if basically the dam operators, if the Corps are sufficiently treating the risks with a high enough standard of care to determine that they're meeting that tolerability threshold. So in our case, you know, when you're in that low probability, high consequence zone, there's not a lot you can do to reduce the probability, the annual probability of failure. So what are you doing to reduce consequences as much as you can? What are you doing to improve risk awareness? What are you doing to improve the kind of stuff that we talked to the EMAs about? Mobilization effectiveness, warning effectiveness.
So if your other 3 TRGs are met, then, and you're in this scenario, then TRG would also be considered met?
I would say likely, potentially, yes. So there is a little bit more play here with the other TRGs than we would normally get. So yeah, I think in this case you can look at the other TRGs and use those as a gauge or a guide somewhat to inform the tolerability evaluation for TRG1, only in this specific case.
And this is just strictly if you're in the low probability high consequence box. This other maybe.
Yes. Yes.
Yeah, okay. All right. So, clear as mud. So Kirk, if you can share your desktop again. So, for TRG2.
Well, before we move on to TRG2, having said that, having said all those words, does anybody think that TRG1 could potentially be met for River Rock?
Yes, I would say my thought would be no, but that's kind of based on TRG2, since we're talking about the interplay of the different TRGs. That would be my thought.
Okay. You're saying you just don't think we've done enough public risk communication? The downstream population is not aware enough of the risks, and we haven't done everything that we can do to reduce consequences?
Yes, that's what I was thinking.
I think that's reasonable. All right, so for TRG2. All right, so unanimously not met. And that's driven by the public, I'm sorry, I'm giving the answer before I'm letting you guys explain what that's driven by. What was that driven by again
So, you know,
for our voting
I'll go back to college, I won't use my teacher.
members?
The lack of communication with the downstream.
Yeah.
Yep.
This is what I do to my kids to try to get to the end result quicker. I shouldn't do that. Okay, so TRG3. So another unanimous not met. What was that driven by for you guys that voted?
The big thing that stuck out to me was the lack of doing that 5-year site-specific dam safety training just by the project personnel themselves. It seems like something that's a fairly easy thing to be able to work in every 5 years, and I mean, I think that goes a long way to just preparedness of the operation of all the staff understanding the proper operation of that dam.
Okay. And TRG4. Unanimous that it's met. What was that driven by for you guys? We're so close, guys.
I just got to talk.
For me, it was the fact that they had completed a lot of their IRRMPs or IRMs, and they only had a couple left.
Okay.
So this one's a little bit interesting, though, because we've effectively said in TRG1 that they haven't reduce risks as low as practicable because there's more we could do on the consequences side regarding risk communication and developing that awareness of potential consequences of the downstream population. And our recommendation for our path forward is actually to pursue a mod study for non-structural measures, which would be potentially considered ALART measures, just non-structural ones. So that's interesting.
Yeah, I think it goes back to what we talked about in the Levee, discussion on TRGs. I think, I think most of the team checked that box in TRG 2 about the risk communication instead of TRG 4.
All right, let's go to path forward.
All right. For various alternatives, structural and non-structural, to reduce risk. Keep us up to date on dam safety training. Risk communication with the public. Erodibility of the spillway. Agree with, right? So in general, do you guys agree with Pursuant and DSMS?
Yeah, I think so. I think they're
Focused on
high enough.
I'm interested in the second to last one. What RMPs are you thinking that we could do to bring down project risk? Somebody made the comment, so somebody has a thought.
I made that comment. I couldn't remember exactly what the RMPs were.
I'm just saying, do you have are you envisioning an RMP that you think could bring project risk down?
I think the biggest one is, the communication with the public downstream. And so it's essentially the non-structural ones where you're improving communication and helping people out.
Okay, so you're thinking more of a non-structural RMP. That's kind of what I was getting at. I was trying to figure out where we were going on that.
Well, so what are we saying with the DSMS?
I mean, what are we saying with the
Like, what do we think needs to?
It would likely be a non-structural.
We can't do that with IRMPs?
But they're not permanent. They're interim risk reduction
Yeah.
measures. So DSMS will be putting in permanent risk reduction measures. Maybe you have a warning system of some kind that you install or something to try to provide warnings better. Like, there's different things you can do to try to get your warning out to the public sooner and more rapidly.
It doesn't seem like there's a lot performance-wise that we can do to reduce the risks.
Right.
I mean, I guess you could you figure out a way to
armor the spillway or something.
Anchor the spillway, like redo the spillway control structure to prevent it from, a similar setup to some of these other ones where we've seen tons of erosion downstream of the control structure, but you didn't lose the control structure, therefore you didn't initiate a breach.
Spillway durations are so long.
True. You got a pretty big block, and
that's an interesting one.
Yeah.
Hey, Bart, did I
Yeah.
hear you say when we go into a dam safety DSMS study, we're only looking at like permanent physical risk reduction measures, so we would never consider like, I guess either communication or just updating documents, procedures, policies, et cetera, as part of a DSMS?
No, I meant like the idea of an interim risk reduction measure is that it's interim, right? It's not necessarily like, it may not be something that we've worked into to our water control manual, if we're talking something associated with that, or it might not be something we wrote into our, just our normal guidance we have for the dam. It can be put in and it can be taken back off. I'm thinking more when you're going to do something, you're going to do something that's going to be, that you're planning to continue to do, not something you're planning to take back away, essentially take back away. So yeah, you're right. Like, we could come back and say, yeah, we still have high risk because you could come back and say we haven't addressed all of our TRGs because we let all the EAPs lapse and everything else, and the project risk could, kind of return back to where it was now. But I think that would be more of us not fulfilling our dam responsibility, not necessarily like we weren't doing everything that we could.
I think a DSMS would be, some type of action.
Yeah.
Not necessarily updating plans and communicating.
No, but communication, non-structural communication can be an outcome of a DSMS in some senses. A lot of times it involves
some type of,
it involves some more advanced warning system that they put in, or something
like not necessarily like
warning
more
system or something like that.
public outreach meetings. Like that's part of our day-to-day
O&M.
responsibility. Yeah. Okay.
Established evacuation routes, those things can be non-structural measures in DSMS.
Okay. Good job, guys. We have been really impressed with all of these presentations, so good job working together and getting this done. Hopefully it was informative for you guys as well.